Very good evening to everyone. Welcome to today's live interactive session on geosynthetics and reinforced soil structures. So, today is the fifth week, and in today's session, we will be solving some of the problems regarding reinforced soil structures. So, the problems that we will be solving today, those problems have actually been taken from Corner's book, okay, and the solution is also from there itself. um, so these problems are actually very much simplified just for academic purposes, right? So original like actual designing of reinforced soil structures actually is quite extensive and quite detailed, but just for uh, this teaching purpose or academic purpose. So these have been simplified and given in corners. All right. So the solution that we will be doing today is by corner or by one problem is from VNS Murthy's book. So those problems are quite simplified versions. All right. And one more thing that I would like to say is that we'll notice that these problems actually do not consider the solution is actually not similar to what was done in the class by the course instructor, because these solutions are actually more simplified, even more simplified than that. They don't consider the seismic effects and other effects also. Okay, these are very simplified, but simplified versions. So just so that the main basic concept, the basic like the uh, totally the basic concept is like clear to you, we will be solving this. And uh, please keep in mind that these are very simplified and these are like solved in one way. Okay, so in exam whenever you do, please consider solving in a more detailed fashion, in the way that these have been solved in the class, in the lectures for you, okay, in the fifth week lectures for you by Professor Rajagopal. So consider solving in that way. And the solution that we'll be doing today is mostly done by corner, overtime corner. So these are more simplified even than that. So they don't consider seismic effects and all those things. So just for a better understanding, so that how we are actually uh, satisfying the pull out criteria, or how we are actually satisfying the rupture criteria, and then how to actually uh, take the length, okay, how to actually calculate the length of the reinforcement. All those things we will be seeing. All right, okay, in a more simplified fashion. Okay, yeah. So these problems have been designed that way that these basic concepts are clear. Okay, how to satisfy the internal stability, how to satisfy the external stability, and then how to design the wall. Okay, so how to select the length of the reinforcement, right? So how you can how to decide the spacing, or how to decide the length of the reinforcement, all those things. All right, so slowly we will be solving this. Okay, step by step we will be starting to solve this. And I request that you also solve yourself, right? So let us together solve step by step. You try to keep a pen and paper with you, and we will be solving it together slowly by slowly. Okay. Okay, so there are some calculation involved, so I request that you also do those calculation by yourselves in the calculator and tell me the results. Okay, so that it's a bit interactive. We'll be solving slowly, step by step. Okay, some problems are like these problems are a little bit lengthy, so slowly we'll be solving. Just we'll be seeing what the steps are, and then we'll be proceeding in the problems. All right. So let us start. Okay, let us see the first question. The first question is design a 6-meter high wraparound type of geotextile wall that is to carry a storage area of equivalent dead load of 10 kb. The wall is to be backfilled with a granular soil, SP, that is poorly graded sand, right? The wall is to be backfilled with a granular soil, poorly graded sand having unit weight 18 kN per meter cube, friction angle of 36 degree and cohesion 0. A woven silk film geotextile with warp direction, ultimate wide width and size strength of 50 kN per meter, and the friction angle of granular soil of 24 degrees is intended to be used in this construction. Okay, so we are to construct a 6-meter high wraparound type of geotextile wall. So wraparound means, if you remember, wraparound means you will be putting one layer and like it's something like this. Okay, you put one layer of geotextile, then wrap it like that. Okay, you put one layer, then wrap it, then other layer you wrap it. So like this you form the wall. So this is nothing but the wraparound type. All right. So we are to construct a wraparound type of geotextile wall, which and that is to carry a dead load of 10 kp. All right. And for that purpose, we are to use a woven silk film geotextile. Okay, we are to use a woven geotextile silk film type. So if you remember the classification and types of geotextile, you can probably visualize that woven silk film geotextile. And in the war, so there are two directions, right? So before I did not discuss this thing, so let me discuss there. So you actually have two directions. One is the warp direction and other is the weft direction. So warp direction is the direction which is also called the machine direction. Machine direction means the direction in which the geotextile is manufactured. So you can consider that it is constructed as a role, right? So the direction along which it is constructed, the direction along which the geotextile is formed in the machine, okay, and then it is rolled, it is passed through the machine and then is kept on rolling, right? So that direction along which it is constructed is nothing but the warp direction, okay. And the other direction, that is the, you can say the shorter dimension direction, that is the width, is nothing but the weft direction. So one is the warp direction and another is the weft direction. So along the warp direction, a wide width tensile strength test was conducted, okay, and that wide width tensile strength test gave a tensile strength of 15 kN per meter. So obviously the geotextile will be giving, it is probable that it will be giving two what to say, two strengths in two perpendicular direction. Okay, two strengths, one in the warp direction and the other in the wave direction, right? So in the warp direction, the strength of the geotextile is 15 kilonewton per meter. Okay, the friction angle of, okay, and this, and so so there is this is the interaction property, okay. So the friction angle between the geotextile and the soil, that is this poorly graded sand, is 24 degrees. So it is roughly two-third of this 5, it is 36 degrees, two-third of 36, which is approximately 24 degrees. Okay, the friction angle between the geotextile and the soil is 24 degrees. The orientation of the geotextile is perpendicular to the wall face and the edges are to be overlapped or sewn to handle the weft direction. That means if this is the wall, drawing the cross section, if this is the wall, the geotextile is laid like this. Okay, so like this geotextile is laid, right? This is the wall shape. Okay, like this geotextile is laid. So this is the warp direction and this is the wave direction, and this, and in the wave direction what you need to do, obviously the wall is long, right? Very long structure, long, like the this out of plane direction is very long, right? So obviously what you need to do, you need to join or to seam to geotextile. So what we are doing is that we are actually uh, giving some overlap here, and then we are maybe sewing it, okay, in the cross machine direction. This is the cross machine direction. All right. A factor of safety of 1.4 is to be used along with appropriate geotextile reduction factor. So this factor of safety of 1.4, where you are using it, we will see. Okay, while we solve it, we will see where we use it. So let us start solving step by step, slowly. So first, what we will be doing is that we will be determining the horizontal pressure. Okay, the horizontal pressure. So how to determine the horizontal pressure? Horizontal pressure means this earth pressure, whatever. Okay. So the earth pressure means the earth pressure and the pressure coming from the dead load or whatever load is other load. So vertical pressure times the earth pressure coefficient, that will give us the horizontal pressure. So that in terms of Z, that is the height, we will be writing that equation, writing that expression downwards. So first, what we will be doing? That's it. Okay. And why are we doing this? Why are we determining this horizontal pressure? So actually, what we want to do, we want to calculate the vertical spacing of the person. All right. So in order to calculate the vertical, the first step is to calculate the vertical spacing of the ring. Okay. So what will be K? So this is how much? 126. Okay. Now therefore the horizontal pressure is what? Component from the earth pressure plus component from the this what is a Q, that is the surcharge. Okay. So K gamma Z plus K into Q. So what is K? 0.26. Gamma is 18. Z we will keep it as Z plus 0.26. And how much was Q? Q was 10. 10. So we are getting this as how much? Let us calculate. 0.26 into 18. 4.68 Z. So okay. So this is the horizontal pressure. Now see, now we are given this ultimate tensile strength. Okay, the ultimate wide width tensile strength is given to us. Now what we need to do from that, we need to find out the what we need to do from that, we need to find out the this allowable tensile strength, right? by reduction factor installation damage into reduction factor for creep into reduction factor for chemical biological damage. Okay, these all are from corners, right? These are all given by corner. Okay, this is corners way of solution. So T allowable is nothing but T ultimate divided by reduction factor installation damage, reduction factor creep, and reduction factor chemical biological damage. Okay, so if we remember, I had shown one table in the previous class, and from that table we can, these values are actually should be determined from tests. Okay, from proper tests this value should be determined, or if you don't have the values, what we can do, we can take a value from the table that I had shared in the previous class. Okay, so from there, so now the what is the purpose here? We are constructing wall, and for walls we will take appropriate values from that table. So this reduction factor for installation damage elastic is just 1.2, 2.5, and 2.7. So 50 divided by how much? 0.2, 2.5, 1.27, 3.81. So it is something that 13 point 13.2. Okay, let's say 13.2. Right, so you got the allowable tensile strength. Okay, now what we need to do, now we will be coming to the main part, that is the determination of spacing. The spacing is to be determined in such a way that this rupture, okay, this what to say, this rupture criteria is actually satisfied. Okay, okay, the rupture criteria is actually satisfied. We will be designing the spacing in such a way. Now if you remember the load, what was the load coming on each reinforcement? That was K times the vertical load, vertical pressure, that will give you the horizontal pressure times the spacing, right? So that would give us, what? That would give us the load coming on each reinforcement layer, isn't it? If you can recall whatever was taught in the lecture, and uh, I think in your assignment also problems were there. Okay, so if you remember, it is nothing but the K, coefficient of the earth pressure coefficient, times the vertical pressure, it will give you the horizontal pressure, times the spacing, that will give you the load coming on each reinforcement, right? And that should be actually the load coming in each reinforcement actually be what? Should be less than the allowable tensile strength, isn't it? The load coming in should be less than what? Right, to prevent rupture, isn't it? The load coming on each reinforcement should be less than the allowable tensile strength to prevent rupture of the reinforcement, isn't it? So what we will be doing is that we will be writing that SV times the horizontal pressure, that is this will give us a load coming on the reinforcement, is equal to TLI by some vector, because it has to be less than it has to be less than the T level, right? So we're dividing that by some factor of safety. And what is that factor of safety? That is given in the question 1.4. Okay, we will be using that factor of safety. So SV is equal to T allow gamma H into factor of safety. So, SV is equal to 13.2 divided by, what is the expression for sigma h? This is the expression for sigma h, right? 4.68 z plus 2.60 times 1.4. So SV is 10.2. Okay, let me not write this. So this is the SV. Now see, as you can see, as z, that is the depth, as depth increases, this SV is going to, we need to provide lesser spacing, because that is quite intuitive, right? We had seen that earlier also, that if the depth increases, obviously we need to reduce the spacing. And why do you need to reduce the spacing? Here is the reason. So you can see, if z increases, obviously this spacing is going to reduce. Now what is the height of the wall? 6 meter. But we are to construct a wall of 6 meter high. 6 meter height. So let us, what we can do is 6 meter high wall, right? So the maximum depth is 6 meters. So now let us find the spacing for 6 meter depth. Okay. So for z equal to 6 meter, how much is SV? Well, let us calculate 13.2 divided by 4.68 into 6. It is 0.307 meters. So we can use 0.30 meter. So below, right, at about full depth of the wall, we have to use a spacing of about 0.3 meters. Okay, now what we can do, as the height increases, as the height, it is from top, if you see, at z, you can see at z reduces. If you are measuring z from the top, we are measuring z from the top, right? So as z reduces, means as we are going up in the wall, what we can do, we can relax this spacing, so that our design becomes more economical. What we can do, we can relax this spacing. So we can increase this spacing from 0.3 meters, right? How to increase that? It is up to you. You have to adjust it according to you. Okay, that is completely up to you, how you want to adjust. All right. So we will be seeing that how to do this. So that is recording on. Yeah. Just a second. Okay. Yeah. So you will be so what we can do is that we can relax the spacing. Okay, as the height of the wall reduces, what we can do, as we go up, we can relax the spacing. Okay, as we go up, we can relax the spacing, so that our design becomes more economical. Now what we can do, let us see, to get to actually to see by trial and error. by trial and error for z is equal to 3.3 meters. What will be the spacing? What will the spacing? Let us see. 0.52 meters. So what we can do, we can use 0.50 meter. So from 6 meters, so if this is the wall, okay, wall height, so you are measuring z like this, right? So this is 0, this is 6 meter. So from here to say here, in this region, what you can do, you can take spacing as 0.30 meter. Above that, what we can do, we can take 0.50 meter. So so we can further increase the spacing. Okay, so again you can see, let us see, let us say for z equal to 1.3 meter, our SV will become 13.25. So if we do this 0.08 meter, 1.0 meter. So what we can do, so we can, okay, so from 6 from here to here we can take spacing of 0.3 spacing. All right, so 6 means 6 minus 3.3 is 2.7. So here to here is 2.7 meters, right? And from here to here, if you are providing a spacing of 0.3 meter, that means 9 layers. Okay, 9 layers. And then what we can do, 4 layers we can provide with 0.50 spacing. Okay, 4 layers we can provide with 0.50 spacing, and the remaining 2 layers, what you can do, we can provide with remaining height. So it will be 9 into 0.3 plus 4 into 0.5, so 4.7 meter already we have covered, right? So 4.7 minus 6, it is, I mean, is 1.3, so 0.65. So remaining 1.3 meters, what we can do, we can provide at 0.65 meter two reinforcement layers. Okay, so total 9, 10, 11, 15, total 15 reinforcement layer we can provide like that. So we can use 0.65 meter. So it is up to you, okay, how to adjust all this reinforcement spacing, that is up to you. Just you need to do some trial and error and check this, check like that and adjust the spacing. Okay, so the maximum depth or spacing is coming as 0.30 meter. So what we decided, we will provide 9 layers with that. Then for 4 layers we will be providing 0.5 meter spacing, and the remaining 1.3 meter height we will be providing 0.65, two layers with 0.65 meter spacing. Okay, this is completely up to you, and you have to decide. Okay, you have to decide the spacing. It is completely up to you. Now let us just draw the diagram. Whatever we have designed, let us just draw it. This is the ground level C. It's very difficult to draw straight. So this is the ground level. So 1, 2. So this is the 15th layer, this is the 14th layer. So these are two layers at 650 mm spacing. Okay, then after that we have four layers at 500 mm spacing. Right, so it will be a little bit less than that. 1, 2, 3, 4. Okay, 13, 12, 11, 10. Four layers at 500 mm spacing, and then we have 9 layers at 300 mm spacing, right? Okay, so we have 9 layers at this 300 mm spacing. So uh, at this point our wall that we have designed like that, that is self-contained, right? It is self-contained. It satisfies the this internal stability requirement, that is the tensile pull out, this rupture and the pull out rate. So the uh, till now what we have done is that we have just satisfied the this rupture criteria. Okay, utilize the rupture criteria to determine the spacing. Now what we will be doing is that we will be utilizing the utilizing this pull out criteria to determine the length. Okay, we will be using the pull out criteria to determine the length of the reinforcement. All right. Okay, so the first part is over. Now the second part. Okay, so we have to determine the length of the reinforcement layers. Okay, that is our target now. Now for that, if you remember, say we just draw this. So this is the Rankine's active wedge, right? So what we need to do is that we need to provide the reinforcement. Okay, so this is the total length of the reinforcement, and this is the length that is within the wedge, and this is the embedment length. So you need to provide the embedment length in such a way that it satisfies the pull out criteria. Okay, satisfies the pull out criteria means that it should not get pulled out due to excessive force coming on the reinforcement. Okay, it should not get pulled out of the reinforcement. The shear force that is mobilized should be enough to resist the pulling out of the reinforcement. Okay, the shear force that is mobilized at the interface of the reinforcement, that is the geotextile, and the soil, the backfill soil, should be enough to resist the what? To resist the force that is coming on that, right? So that shear force mobilized should be enough to resist the force that is coming on the reinforcement. Okay, so that it does not get pulled out. So we will utilize that criteria to determine the embedment length and then the total length of the reinforcement. Okay, so now what we can do is that, so this reinforce, if you remember, what we can write is that LE, it is the embedment length, it's nothing but into factor of safety by so this part 2C plus gamma Z tan delta into LE, it is nothing but the what? Nothing but the shear resistance that is developed at the interface, isn't it? It is nothing but the shear resistance that is developed at the interface. So what will happen when there will be a tendency for the so some loads will be acting on this reinforcement, right? So these loads will try to pull the reinforcement out of the layer. That pulling out should be resisted by the friction or the shear force that is developed at the top and the bottom of the layer, bottom of the reinforcement layer. Okay, and that should be actually resisted by this embedment length, that is the length of the reinforcement that is outside the active wedge. That is what it is holding the active wedge in place, right? If this length is not present, then what will happen? This will just slide on its own along with the reinforcement. There is no use of putting the reinforcement, isn't it? Isn't it? That will just slide on its own. There is no point of providing the reinforcement. So you need to provide some embedment length, right? So that it holds the soil in place. So this 2IC gamma Z tan delta into LE, delta is nothing but the friction angle between the reinforcement and the soil. That can be determined from shear box test. Okay, that we need to determine from shear box test. So this twice C plus gamma Z tan delta into L is nothing but that shear force that is mobilized. And what is this SV into sigma H into sigma H? That is the SV into sigma H is nothing but the force coming on, the load coming on which reinforcement. So what we are doing, that load we are multiplying with some vector of safety, okay? So that our length, whatever we are calculating, is little bit higher. So we are in more conservative side, okay? Safer side, isn't it? So now we are, so first what we did, we determined the spacing using the tensile rupture criteria, where the load coming, this same load SV into sigma H should be actually less than what? That load coming should be less than the tensile strength of the geotextile. Right? Now what we are doing? Now this load coming should be actually less than the frictional resistance or the shear force or the pull out resistance that is mobilized at the interface of the reinforcement and the soil. Alright. So SV times this is, what was the sigma h if you remember, into 1.4, c is 0, 18 into z, 1024. Okay, all right. So from here we can write is into 6.55z plus 3.64 divided by 16.0 z. This is this LE. Okay, the embedment length. And what is this LR? How to determine this LR? This LR can be, so this is H, sit, sit, and sit. This is Z. So how to determine this LR? You know this angle 45 minus 5 plus 5 by 2. So this one will be 45 minus 5 by 2. So this LR will be H minus Z, 10, 45 minus 36 by 2. That is 6.0 minus Z into 0.509. This is the expression for LR. So we got LE, we got LR, right? So if we add these two, we will be getting the length of the reinforcement. Okay, at LE you can see this embedment length is varying with depth Z and also with spacing. Okay, it is varying with the depth and also varying with the spacing. So now what we have to do, we need to make one table. Okay, table to determine the this length of each reinforcement. All right, so we need to make a table now. So the first, what should I do? What I can do is that I think, well, if let us do it like this manually. We can do in the Excel sheet later. Okay. So the first column will be layer number. Just write it. Layer number, then depth Z meters, vertical spacing in meter, then calculated LE, then LE minimum, okay, is in meter, then calculated LR in meter, then L calculated in meter, and L specified in meter. Now can you tell me what is LE minimum? Can you tell me what is LE minimum? What is the minimum embedment length that we should provide? This LE minimum, what is this? This is the minimum embedment length that should provide. Okay, whatever our LE comes out after calculation, if it's less than LE minimum, what we will be doing is that we will be providing LE minimum only. This is the minimum embedment length that we should provide. So what is the minimum embedment length that we should provide? I know answer. This has been discussed in the lectures. Okay, this has been discussed in the lectures. So what is the minimum LE that is to be provided? As per codal provisions, what is the minimum embedment length that we should provide? Please recall what was discussed in the lecture. What is the minimum embedment length that should be provided? Please try to recall. The minimum embedment length that we should provide is how much? That should be 1 meter. Okay. As per total provisions, the minimum embedment length that we should provide is 1 meter length. Alright. So now let us calculate for layer by layer. Let us calculate. Okay. So we have how much? How many? 15 layers. Try to. Uh, okay. Okay. So layer is 15, 14, 13, 12, 10, 7, 6, 5, 4, 3, 2, 1. Okay, so all these layer numbers we have put. Now what are the depths? Please tell me. Please see from this image and tell me what is the depth of layer number 15 from the top. What is the depth of layer number 15? What is the depth Z of layer number 15 from here, from the ground level? Sorry, from the top level. What is the depth of layer number 15? What is the depth of layer number 15? What is the depth from the top? See, these are spaced at 0.65, so 0.65 meters. So from here to here, what is the distance? 0.65 meter. From here to here, it's again 0.65 meters. So from the top, it will be 1.3 meter. Then from 1.3 meter plus how much? 0.5 here. So layer 13, 1.8 meter, isn't it? So like this, what you need to do? You need to take write all the depths. So layer 15, 0.65, 1.30, 1.80, 2.30, 0.80, 30, 3.60, 90, 4.20, 50, 0, and 6.0. Alright. Now what were the spacings? From here it was 0.65, here it sorry. It was 1.65, then it was 0.5, 0.5, 5, 5, then all were 0.3. And one more thing, why are we taking this to calculate the load on the reinforcement, load on in each reinforcement layer? Why, can you tell me why are we multiply this SV with sigma h? If you recall it from the lectures, this SV, what we take, say this is the reinforcement layer, right? So half above and half below, we say that this much layer of soil will be actually contributing. So total is SV, and say, so earth pressure, some earth pressure will be coming, say some earth pressure is varying like it, so it is, so it's like this, right? So earth pressure, lateral earth pressure times this SV. SV will nothing will, it will give the average. Okay, so if you take this earth pressure times this SV, it will give the average earth pressure times the SV. It will give us the load. Okay, so we consider that the SV by 2 above and SV by 2 below, these soils actually contribute to the load of the reinforcement. That's why I'm multiplying that by SV. Now, so SV we wrote. Now let us calculate. So we got Z, we got SV. Now we can calculate LE from LE using this equation. LE using this equation. Now let me just open one Excel sheet. Okay. Can we open from here? Just a second. It will be easier for us to do the calculation, right? An Excel sheet. How to exit? Just open an Excel sheet. I will share this share the screen. Okay, just a second. Okay, this is visible, I hope. So we have layer Z, SV. Okay, and we are finding LE. So we have 15, 40. We have 0.65, 0. Sorry, 0, 80, 0.80. Point plus 5. Right, and then we have the spacing. Spacing is 0.65, 0.6, sorry, 0.65, 0.5044, and we have 0.30. Now what is the expression for LE? equal to SV divided by 16 times Z into 6.55 times Z plus 3.64. Did I do some mistake? SV times 16 into, just a second. SV means how much? 0.65. So 0.65, 16, 0.65 times 6.55. 0.49 it should come. Did I do something wrong? So, let me write this down again. SV SV times 6.55 times Z becomes Z plus 3.64 divided by 16 times Z. What mistake am I doing? SV is 0.6. SV times 6.55 times Z plus 3.64 by 16 times. Okay, now it's correct. Okay, so these are the LE values, but what is the LE minimum? LE minimum, as you know, should be 1 meter. Okay, so LE minimum should be 1 meter, right? So these LEs are coming less than LE minimum, isn't it? These LEs are coming less than LE minimum. So we need to provide this LE minimum, this minimum embedment length. The embedment calculated embedment lengths are coming to be less than this, less than the minimum required. So what we need to do, we need to provide for this minimum embedment length. Now LE we determined. So the next step is to determine LR. Okay. The next step is to determine this LR. So LR is H minus Z 6 minus z times 0.509. Okay. So this is the LR. Now L calculated. L calculated is nothing but LE plus LR. Okay, LE here, LE, all LEs are less than LE minimum. Alright, so minimum we have to provide. So what we will be doing? We will be doing LR plus LE minimum. So these are the calculated L's. Okay. Now what we can do, up to some height we can provide one this one length, and then up to other height we can provide one length, and up till other height we can provide other length. Okay, so we can subdivide. So providing different length for each layers is difficult, right? Because you need to shape, you need to measure and cut the reinforcement in such a way for each layer. That is a little bit difficult. So what we do, we divide the complete wall in some blocks, and we fix the length for some blocks. So here what we can do is that for lower layers, okay, from layer 1 to 7, what we can do, for these layers what we can do, we can provide 2-meter specified. Okay, well calculated, 2 meters. All right, and then for layers 8 to 12, what we can do, we can provide 3 meters. 8 to 12 here we can provide 3 meters, and for the above top 3 layers, what we can do, we can provide 4 meters. Okay, okay, so this actually completes the design part. We are in meters. Alright, so what I will do, I will just paste it. So I will just paste it here. Okay, okay, just a second, I will reshare the screen. So we got the lengths. Okay, all right, so for each layer, and then we selected this final length. All right, so this now designing part is over. Now what we need to do is that we need to do the stability checks, the external stability. The internal stability criteria, was already satisfied, right? So we already did our solution. We already did all the solution by satisfying the internal stability criteria. That is the rupture criteria and the pull-out criteria, isn't it? Now what we will be doing is that we will be doing the final external stability checks. External stability checks, if you remember, what were those? Sliding, overturning, and bearing capacity. And also the fourth check is there, that is the slip circle failure. That is a little bit difficult to do because we need to do it maybe using the software and all. By doing in hand, it's actually very difficult because we need to consider many slip circles and do that thing. So we'll be just doing this first three checks, and fourth we will assume that the fourth one is satisfied. Okay. But in practice, we always have to do all these four checks, including the slip circle. This check, okay, including the slip circle check. Okay, before doing the check, one more thing that I want to mention is that, see, now we are, how are we providing the reinforcement? How are we providing the geotextile? We are placing it in the warp direction, right? In the machine direction. So this is the one, like this we are, like this we are placing it. This is the machine direction or the warp direction. Now, if the calculated L length, this L length that is calculated, that L length is actually uh, lesser than the width. Okay, so this is the length direction of the geotextile. This is machine direction. This is how this is rolled. How the geotextile is rolled. This is that direction lengthwise, and this is the width of the. Now, if this width, this is if calculated, this calculated length is actually less than the width, then what we can do? We can also place the geotextile like this. Okay, that is, in the, if you place it like this, then what will happen? This weft direction, this is the cross machine direction, this weft direction strength will be utilized. But generally what happens, this L is calculated length is actually greater than the width, so generally it is placed like this only and not like that. So what we are doing here, in our case, what we are doing, we are placing the geotextile like this, right? We are placing like this in the warp direction, and proper overlap or proper, it has to be given, and the geotextile has to be sewn together. Okay, so proper overlap should be there between the geotextile, and also it should be shown. So proper joint should be there between the geotextile layers that you will be placing. All right. Now it is recommended that a minimum overlap length of approximately 1 meter has to be used. Okay, so let us calculate that overlap length. So this A part, what we did, A part we did this we can satisfy the determine the spacing. In the B part we determine this embedment length. Now we are coming to C part. In part C we will be checking for this overlap length. Okay, check for overlap length. Now see, this is the so these are actually overlapped, like see, side by side. How I cannot draw this, right? So say this is like this, wall is like this. Okay, wall is like this, so these are overlapped like this. Okay, so these are overlapped like this. So this is the overlap distance, that is L. Now this is the wall shape. These are the reinforcement, RFT1, this is RFT2. This is the overlap length. We are checking for this overlap length. Now since here the overlap will be something like that, right? So four surfaces, 1 2 3 4. Okay, 1 2 3 4. So Here we will be using a similar expression what we used for this, okay, for pull out, but with a little change. What is the change here? Be 4 times CA set delta, and this CA is nothing but the addition between the two layers. Okay, this CA is the addition between the two layers, or this layer and the soil, not the two layers. Actually, it is the addition between the reinforcement layer and the soil. So SV into 4.68 Z plus 2.6 into 1.4 0 plus 18 into Z. Very, what's wrong, man? Wait, just a second. Yeah. So 18 into how much? 18 into Z, 10, 24. Now for so this overlap is actually maximum at the uppermost layer. All right, it is maximum at the uppermost layer for Z equal to 0.65 meters. Because obviously since Z increases, L naught is going to reduce, right? So it is going to be maximum at the uppermost layer. So uppermost layer Z is 0.65 meter, and spacing is also 0.65 meter. So meter. So we can calculate this L naught as 0.25 meter. So it is coming out to be 0.425 meter. So use 1 meter throughout. Alright, so generally a minimum of 1 meter of this 1 meter overlap has to be used. Okay, so we'll be using 1 meter overlap throughout. Now done. Now we already did the internal stability, we satisfied the internal stability requirement, we checked for the overlap length. Now comes the final part, that is the external stability check. Alright, just add some more pages. Okay. Now let me just draw the diagram again, okay, because that is important, and the properties for the Okay, so this is the wall. Here to here. First two layers 1.8 meter. Then here to 10. 2.1 meter. So total is 6 meters. Right. Now what were the lengths that we provided? If you remember, for the first three layers it was 4 meter. So these layers it was 4 meter. Sorry. Let's put it here. Four meter. Then we had 3 meter and then 2 meters. 3 meter for 13, 12, 11, 10. 13, 12, 11, 10. Okay, so these are then we had 3 meter. Where should I write? 2 meter. Alright, so these were the different lengths. Okay, lengths of reinforcement that we provided. I will just write the properties of the backfill. So backfill soil, gamma is equal to 18 kilonewton per meter cube, delta is equal to pi is equal to 34 degrees. Okay, and foundation soil, is gamma is equal to 18.5. Approximate. Okay, this is approximate. You can take 14.2 degrees. 20 cohesion. So radiation we can take approximately 0.8 C 16. Okay, now first is the sliding check. Right, the sliding. What I am seeing here is that the solution that is given in Corner's book. In that solution, what they did was this lengths are actually not. See if you can see this 4 meter, 3 meter. These lengths are actually not uh, matching. Just a second, okay. The diagram and whatever they have drawn. This diagram, whatever they have drawn. See what we provided. We provided for the first three layers. We provided four, right? But here you can see only first two layers they have considered this 4 meter. Okay, so there I think there is some mismatch in the solution and in the problem in the solution that they provide. So whatever we will following this solution, what I suggested that you do this part again by yourself. This is very easy. We will see now. This part is quite easy to do. So you can just redraw this figure again as per whatever you have designed here as per this table, whatever you have specified, and then what you can do, you can again try to solve it. All right, you can again try to solve this part. I will just follow, but what I will be doing is that I will be following this only. I will be following this. I will write a review this part here onwards. Okay, so redo this part yourself from here onwards. All right, but what I will be doing is that I will be following this only, just to show you how all the calculations are done, so that you can do it yourself correctly. Okay, because what I see here, what they have done here, what they have chosen here, this lengths and all these are not correct. This do not agree with whatever results that we have specified here. All right, so what I suggest, you do it by yourself again. But now what I will be doing, that I will be following this only and just showing you how to do the calculation. All right, so yeah, so this backfill soil, so as you know, due to this backfill soil there will be one active thrust on the reinforced soil block. So we are assuming that PA is actually inclined at an angle delta, the horizontal. And where will be this PA acting? One third of the height, that is 3 meters from the bottom, right? 3 meters from the sorry 2 meters from the bottom. 2 meters from the 6 by 3 is 2, so 2 meters from the bottom. Now let us calculate. So k is 1 minus sine phi by 1 plus sine phi. Now here what is this phi? Phi is the backfill soils phi, right? Phi is the backfill soils phi. So 1 minus sine 34 by 1 minus sine 1 plus sine 34. For the backfill soil, this phi is 34 degrees, and for the reinforced soil, the phi was 36 degrees, and for the backfill soil is 34 degrees. This will be 0.28. Now what is PA? Half gamma h square k, so 0.5, 18, 6 square, 28, 0.7 kilometer per meter. Now, so what will be the components? This one will be the cost component, one will be the sine component, right? So PA cos 34 So you can see here no earthquake forces and nothing they have considered. They have just simply solved it, okay, in a very simplified way. Just for the understanding purpose of understanding, they have just solved it. But while you solve in your exam, while you do the solution in your exam, follow what however it was done by Professor Rajagopal in the class. Okay, follow what method that was taught to you in the class, considering all the factors. Okay, 3 or 4 problems were solved in the class in Big Five, so follow that procedure. All right, don't follow this procedure because this is very simplified. Whatever that is given in corners. All right, so follow the procedure whatever that was taught in the class. Right now, what is first of a factor of safety in overturning? So there is nothing but resisting moment divided by the driving moment. So what will be the resisting moment? So the weight, the moment generated by the weight, that will be what, that is what will be resisting the overturning, right? So resisting moment will be W1 x1 plus W2 x2 plus T3 plus A sin delta into how much, 4. Wait, I will explain you, okay, one by one. Let me just write it down, explain it to you one by one. Now this W1, W2, W3, what are these? These are the weights of each soil block. Now what are these soil blocks that I am talking about? These are these. So the W1 is nothing but this soil block. Okay, W1 is this soil block. W2 is this soil block, and W3 is this soil block. This soil block. So understood? This is W1, this is W2, and this soil block is W3. So we have divided the reinforced soil total block into 3 small blocks, W1, W2, and W3. So W1, this weight into x1. What will be x1? The center of this rectangle, that is 1. Then next time when we do, we are taking moment about this point, right? Again, W2 means this weight multiplied by center. This is 1 meter, so 0.5. This is 2 meters, so 2.5. We will be multiplying this with what is the lever arm? The lever arm is 2.5. And for this soil block, what is the lever arm? Again 1 meter, so 2 meters, 3 meters, 3.5 meters. It will be 3.5 meter. That means from here to here it will be 3.5 meters. Alright. So now let us write. So first soil block is 6 meter high and width is 2 meter. So 6 meters into 2 meters into 18. 18 is nothing but the unit weight. So 6 into 2 into 18 into 1. X1 is 1. For the next one, what is this side? 3.9 from here to here. 3.9. So 3.9 with this 1 meter to 18 into lever arm was 2.5. Same W3 1.8 into 1 into 18 into 3. Okay, and PA, this one you already determined, 50.7 into 4. Right? So from here, this will be acting here. From here to here, it's 4 meters. Not here, actually here. Acting here. Divided by PA cos delta 75.2 into 2. Alright. So we'll see the factor of safety overturning comes out as 4.7, which is actually greater than 2. So acceptable, right? So typically for reinforced structures, generally this this overturning factor of safety is generally satisfied easily. Okay, this is generally very easily satisfied. There is no problem in it. Generally, it is automatically easily satisfied. It's overturning factor of safety. Now, sliding factor of safety, same. So here, what we will be doing is that CA into L plus W1 plus W2 W3 sin delta L delta into L. So here, what we are doing, we are just averaging that this uh, see this W1 W2 what will be in kilonewton, right, in load terms, divided by length. It is the length of the soil block that is in contact with the foundation soil into tan delta will give the horizontal. So this is the vertical times tan delta will give me the horizontal, and CA times L, that is the adhesion times length, that will also give me a horizontal. So this total is in kilonewton per meter, right? That times the length again will give me in kilonewton divided by PA cos delta. Okay, that is the resisting. So this is a driving force. Now CA into L means what is the CA? 16. What is L? L is the length that is in contact with this base, that is 2 meters. Okay, from here to here is 2 meters. Right? This is what is in contact with the foundation soil. So 2 meters. So CA is 16 into 2 plus W1. W1 is nothing but 6 into 2 into 18. W2 is 3.9 into 1 into 18. W3 is 1.88 into 1 into 18. Okay, so we will just I will just write this down. Times 2. And this will come out as 2.1 5, which is okay. Now sliding down, overturning done. Next is my bearing, this bearing capacity check, bearing failure check. Okay, so what that so generally you have to determine this by this Terzakis, this IS code formula or whatever, right? IS code method or whatever. So we are just using here this normal Terzakis formula for this simplification. Okay, but whenever you do, Q is 0 because this depth of foundation is 0, because the whole soil is resting directly over the foundation soil, right? Plus 269 square. Now what is the P acting? Pressure acting 18 into 6, right? Total height into 8, 6 meters into 8 plus the dead load. Factor safety is 5, sorry, 269.18, which is again acceptable, right? So both internal external designs are complete now. First we chose the, so let us just go one by one. Okay, how we did. So first what we did, we determined the spacing How did we determine the spacing? We determined the spacing by following the rupture criteria. Okay, by not allowing the rupture to occur, by following that criteria, we determined the spacing. Then what did we determine the spacing and provided optimum spacing. After that, we determine the length of reinforcement layer. How did we determine the length of reinforcement layer? We determine the length of reinforcement layer by satisfying the pull-out criteria, right? Provided the layers. Then we checked for the overlap length. We calculated the overlap length. We checked for that. After that, we came to the external stability. We checked the external stability for overturning, sliding, and the bearing. Okay. So this way, our total design is now complete. All right. Okay, so this was a very simplified design. Okay, very simplified. There were no live loads taken into consideration, live loads due to traffic or other things, no earthquake loads, seismic loads that were considered. Just a very simple design, so that the basic how we are doing it. Okay, how what criteria we are satisfying to determine what, how all criteria are satisfied, and how we are doing the stability check, so that the basic this concept is clear. For that reason, we solve this problem. All right, now so this was one more problem. What we will be doing is that, let us, so this problem is also quite long. So what we will be we will be doing is that, let us solve this in the next class. Okay, we will be solving this problem 2 in the next class. Let us go to this problem 3, because this will be little bit shorter, I think, smaller. So in 20 minutes probably we will be able to finish them. Okay, and this problem will be solving in the next class. Now let us come to the problem. A typical section of a retaining wall with a backfill reinforced with metal strips. So now, so before we solve the problem for reinforced with geotextile, here we are having some facing blocks are used, and we are using metal strips. Okay, metal strips are used. The following data are available. The height is 9 meters. The width, it is the width of each metal strip is 100 mm. So 100 mm width metal strips are used. Width is 100 mm. Thickness of each metal strip is 5 mm. The yield strength of the this metal strip is 240 MPa. This is mild steel. Okay, 240 MPa. Factor of safety for steel is reduction factor, that is 1.67. Factor of safety on soil friction is 1.5. Friction angle of the soil is 36 degree. Unit weight is 17.5 kilonewton per meter cube. Uh, the this 25 degrees is actually what, the delta. Okay, this 25 degrees is nothing but this delta. Okay, between the soil and the metal strip. Okay, this 25 degrees is the friction angle between the soil and the metal strip. Then SV into SH is 1 into 1 meter, means the vertical spacing to the horizontal spacing. So these are strips, right? So this horizontal spacing also matter in that case. So the vertical spacing and the horizontal spacing are 1 by 1 meter. All right. So what are required? The L and the LE at varying depths, the largest tension in the strip, the allowable tension in the strip, and the check for external stability. So let us do one by one. So here actually we will be solving it in a different way. What method we used for the previous problem? A little different way will be solving this problem. Okay, so let us start. Now, what is the vertical, this horizontal pressure that is coming? sigma z into K. Right, this is the horizontal pressure. There is no Q. This is the horizontal pressure. The load coming on reinforcement is nothing but okay, gamma h times SB into SH. Before we are determining per meter, SH is to be 1 meter. Okay, here SH can vary, but in our problem here SH is 1 meter only. But in general, when you are using steel sticks, SH might can vary. Alright. So SB into SH. So T, what is Ka? Okay, so this will be 4.55 Z kilonewton per strip. Okay, that is the tension, that is the tensile load that is coming on each strip. Okay, that is the tension that is coming on each strip. Now, similar to the previously whatever we had done, press into T. This will satisfy the pull out rating. Okay. Now what we will be doing in place of this T, we will be putting this expression. Okay. So 1.5 this is given. Yeah. So this is given. Soil friction is 1.5. Vector safety on soil friction. This is given, right? So in place of T, whatever what we will be putting is there. I said. So here what we are doing is that we will be providing spacing in the length. We will be calculating in such a way that both of these will actually be satisfying the load. This is the rupture criteria and the pull out criteria. All right. What is Z? Z is okay. 2 into gamma into 0. Z is Z. We'll put Z. Okay. 0.1. B is how much? B is the width. B width is 100 mm, means 0.1 into 10 delta means 1024. 1024 into Z. So Z will cancel out. 10 20 1.5 into 4.55 2 into 17.5 into 0.1 into 0.47. Okay, so LE will come out as 4.14 meter. So now you are seeing is that this LE is irrespective of its height. Okay, it's not dependent on what? This LE is independent of this height Z. So 4.14 meter fixed LE which is constant with the depth. Okay. Now if we see the figure, yeah. Now we can see for this 1 to 9. Okay, 9 strips are used. So we can see the position of the strips from 1 to 9. Okay, so each of this block, each of this facing block is 1 meter height. Okay, and the first strip is placed 0.5 meter below the ground level or the top level, top surface. All right, so it is placed 0.5 meter below the top surface. The spacing The spacing is kept spacing between the strips is kept at 1 meter. Okay, it is kept at 1 meter, but and the first and the last strips are 0.5 meter from the ground levels. All right. Now what we can do? Now what we can do? We can now see, this is a different. This is a little different way of solving, satisfying the criteria, the stability criteria. So, internal stability criteria we already satisfied in this part, right? The internal stability criteria we already satisfied in this part. The tension criteria and the and our this pull-out criteria. Now, what we will be doing is that we will be trying to satisfy the external stability criteria. Before that, what we will do is that we will check that the maximum this tension, the maximum tension that is coming on all the strips, total combined tensile load that is coming on all the strips is actually less than or equal to the active thrust. Because see, active thrust is what that is pushing the wall outwards, right? These active thrust should actually be taken care by the this tensile load that is coming on each layer, right? This active thrust is actually divided as load into this each reinforcement layer, isn't it? This active thrust which is acting on the wall, that is divided into each of these reinforcement layers, right? So let us just check that once, whether that is actually divided or not. So what is the total tension that is coming? What is the total tension that is coming? It is nothing but uh, what to say, this all the heights, sum of all the heights, say. So if you see, there are 9 layers, right? So what is the height? First one is 0.5 meters depth, say, then it is at 1.5 meter, like that, right? So we will write this. So 0.5 plus 1.5, 0.5, 3.5, 5, total 9 layers, right? So 0.5, 1.5, 2.5, 3.5, 4.5, 5.5, 6.5, 7.5, 8.5. 8.5, 6.5. Okay, so depth into the spacing is 1 only, 1 into the friction is what? Sorry, into K. So how much is K? K is 0.26. Okay, so how much is that? Okay, not like that. See, what we can do is that just a second. This is what? This is summation Z, right? So summation Z times 4.55. So if you remember, what was our T? Our T was 4.55 Z. So our T was 4.55 Z. So summation T will be 4.55 summation Z. So what is summation Z? Summation Z, you understood. Z means the depth of each layer. So the sum of the depths of each layer times 4.55. So 0.5 plus 1.5 plus 2.5 plus 3.5 plus 4.5 plus 5.5 plus 6.5 plus 7.5 plus 8.5 equal 1.55. 40.5 into 4.55, 40.5 into 4.55, 184.27 meter. Right. So this is the this tension in per strip. So in all the strips, this is the total tension. Okay, total tension, that tensile load that is taken by all of the strips. And let us calculate PA. PA is half kh square. So half 17.5 into 9 square into what is K? 2.26. So it will be same 184.28, which is equal to summation T, right? So total PA is actually distributed as tensile load on each of the reinforcement, right? Just a cross check, okay? Just a cross check, back calculation, nothing else. Okay. Now what is the maximum? So now where shall we be getting the maximum tension? The maximum tension will be where will it be coming? So the maximum tension will obviously be coming at the lowermost strip, that is the ninth strip, the bottommost strip. There the maximum tension will be coming. Okay, the ninth most at the bottommost strip, in that strip the maximum tension will be coming, right? So tension is gamma z k 5. What is z? 8.5 for the ninth strip. It is 8.5. Z is 8.5. So what is that? How much is it coming? 17.5 into 8.5 into 0.26. 38.68 kilometer. So that is bottommost. So out of this total tensile load that is distributed among all the strips, the bottommost strip takes 38.68 kilonewton out of the this 184 kilonewton. Out of this 184 kilonewton, 38.68 kilonewton is taken by the bottommost. Now let us find out the allowable tension. T allowable is F allowable into thickness into width. Okay, so what is F allowable? F allowable is 240 mpm into 10 to the power 3 divided by 1.67. This is given, right? Factor of safety for steel, it is given. So it will be 143.7 into 10 to the power 3 kilonewton per meter square. This is Fa. Therefore, T allowable is equal to 143.7 into 10 to the power 3 into thickness was 5 mm and this was 100 mm. So how much will it be? 143.7 into 10 to the power 1000 into 100. 70, approximately 72 kilonewton. Okay, this 72 kilonewton is greater than 38.68 kilonewton, right? So this is the allowable, this is the tensile strength. Okay, this is the tensile strength of the reinforcement. Now this tensile strength of the reinforcement is greater than the maximum tensile load that is coming on the reinforcement. Okay, so this is okay. Now total length. Now total length of strip you know is nothing but LR plus LE. So what is LR? H minus Z 1045 minus 5 by 2 plus LE. LE was fixed. We already calculated LE. LE is independent of depth in our case and it comes out as 4.14 meter. Okay, LE is independent of depth and it comes out as 4.14 meters. Okay, now from this expression what we can do, this h is 9 meter, right? So for each z, we can determine the total length. Okay, so you can do this by yourself and then calculate the total length. So you will see that it is already given here in the figure. It will come somewhat, it will come out like this. Okay, somehow the arrangement will be something like this. So they have provided the lengths and they have divided into these two blocks, as you can see here. So like this, they have this arrangement they have followed. All right, so you can calculate for each step. You can similar to the previous one. You can make a table and you can calculate the L, and you can provide as per your choice. You can provide the total length. Okay, total length of each reinforcement. All right, now comes this external stability check. Okay, now comes this external stability check. Now first is the sliding. So what is the vector safety in sliding? Resisting by this driving force. Okay, now what is the resisting force? W10 delta. W is the total weight. Okay, total weight. So 5, that's what we are doing here. 17.5 to 9 to 36. So this is the weight into 1036. So if you see the figure, so wait a second. So what they are doing is that they are just taking this average width. Okay, so average width 4.5 plus this 8.5, 4.5 plus 8, see 4.5 you can see here, this base. So this they are taking, okay, this they are taking this 4.5 plus this 8.5. Okay, this 4.5 plus 8.5 by 2, this average they are taking, times the unit weight 17.5 into 9 is the height, times 10 delta. It will give us the uh, this total weight of the soil mass. All right, and this 4.5, actually see this 4.5, this is just taken. Okay, just this is your choice. The minimum width at the bottom, minimum width is 4.14 meter, right? So this strip will come to 4.14 meter. Minimum it has to come up to 4.14 meter. Okay, minimum it has to come up to 4.14 meter. But what they are doing is that minimum they are providing 4.5 meter, and that will actually, so they are choosing the foundation also such that it is up to 4.5 meter. All right, so this is up to completely up to your choice. All right, so yeah, so yeah, so average width, the top width times the bottom plus the bottom width, average width times 17.5 unit weight into 9 is the height times 10 delta. It will give the resisting force, and this will come out as 744 kilonewton. Now what is the driving force? Driving force is nothing but PA, and what is the PA? We already calculated. PA was this. So what is the vector of safety in sliding? 744 to 8.5 is okay. Now next is for overturning. Vector of safety in overturning, sigma resisting moment, overturning moment. Now say again let us find out the resisting moment, 4.5 into 9 into So see, initially in the previous problem, what we did, we divided it into certain blocks and did, right? Here also they are almost doing the same thing, but this, uh, what to say, this distribution, what they have done is it will be different. Okay, this distribution, what they have done is it will be different. So first, what they did, first they took this 4.5 meter block. Okay, and then what they did, they took this triangle. Okay, this first they chose this 4.5 meter block, and after that they instead of taking these rectangles, these two rectangles, what they did was they took this triangle instead. In our case, what do we did? We took three rectangles, right? This, and this. But in their case, what they did? They took this first rectangle, soil block, and this second triangle. All right, like this, they calculated the weights and the overturning this moment. All right. Okay, so I hope you understand this part. Okay, you understand these parts. Okay, this is the weight of the first block, weight of this width of this block, and this other part they have considered this as it is triangle. Okay, so the weight of that, so 1 2, these two weights are here, and times the lever arms, that will give you the resisting moments. Weights times the lever arms, these are the lever arms, that will give you the nothing but the moment. Alright, so total resisting moment comes out as, and what is the overturning moment? It is PA into H by 3. Factor of safety in overturning. This. Okay. Alright. So sliding factor of safety we checked. Overturning factor of safety is checked. So next, what you can do is that you can do by yourself is you can find out this bearing capacity. Okay, factor of safety in bearing. Okay, that you can do by yourself. For the original count, you can see phi and gamma are given. What we can do, you can calculate the vertical loads, and then solve the. So if you see, if you remember the what first problem we solved, the vertical load calculation, all these were very simplified. But if you remember the solution that was done in the class, how whatever that was taught, so that was little bit different, right? That was little bit different. So you all solve using that method only. What you can do, you can take the problem, okay, take the question, you can take the question from here, and you can solve using that method. You can consider some seismic loads also. Then also, as you can see, the vertical load calculation, this RV, L minus 2IC, all these things like that, this vertical pressure was determined. But in the first problem that we solve, we not use these things, right? So what you can do is that you can solve this by yourselves. You take the question from here and you solve using that technique, whatever that was, the however that was solved in the class. Okay, in whatever method it was solved in the class, you try to solve with that technique. Okay, following the this provisions, model provisions, or this BS provision, BS code provisions, or that highway provisions. Okay, okay, you try to take the question from here and solve. You see how the problems were solved in the class. In that method you try, because in the exams the questions will be set in that way that you need to solve in that part. These problems that we are discussing today, these are highly simplified versions. Okay, these are very simplified versions just for basic understanding. All right, just for basic understanding, these are solved this way. Okay, but when you solve in exam, you solve in a way that was taught in the class. All right, so for this you do this bearing capacity check also, okay, by yourself. All right, so with this we end today's class. So next class we will be solving problems on reinforcement of embankments. Okay, reinforcement of embankments using geotextiles or geogrids. We will be solving that part, and also we will be solving one more problem. This problem 2 that was left, we will be solving that problem. All right, all right. So okay, and I hope these basics were clear from these problems. Okay, these were meant for that purpose only. Why are we doing what? So that thing should be clear. How we are choosing the spacing, whatever, why, how we are doing everything. Those things should be clear, and the purpose of this was that one. But again, I want to repeat that, solve the problems again, solve all these problems again, take the questions from here and solve each of these problems again using the technique that was discussed in the class lectures, in the main lectures, whatever that were discussed by Professor Rajagopal. Use that technique to solve the problem. All right, okay. So one problem is left that we will be solving in the next class, and we will be solving other problems uh, that dealing with this stabilization of embankments. Okay, stabilization of embankments, and then as we progress in the course, we will be solving some. We will be dealing with some other functions of this geotextile, such as filtration function. All those things we will be solving easy basic problems from that also later as we proceed. All right. So before we end, let us just go through this problem once again. So what we did, we determined the load on each reinforcement. Okay, this load in reinforcement directly put in this term for this LE, that is the embedment length. From there we got the embedment length. Okay, hereby we satisfied the tension criteria and the pull out criteria. Then we checked that the total, whether the total tension, that tensile load is transmitted, is equal to the PA or PA, that is the active third pressure or not, that we checked. Then we determine the strength of the reinforcement, the tensile strength of the reinforcement, allowable strength of the reinforcement, and we check that whether the maximum load that is coming on each reinforcement is less than that or not. Okay, we check that here, and in the end we determine the length of the reinforcements, and then we determine the factor of safety in overturning and sliding. And you do the factor of safety for that bearing. You do by yourself. You did by yourself. And what you do, these two problems, the questions you got, you solve these questions using the technique that was done in the class. You consider some seismic loads, you consider the all the codal provisions that were given by this, that were discussed in the classes, BS code provisions, or the national highway this administration provisions. All these provisions you consider and you solve. Okay, in whatever way that was solved in the class, because in exam you need to solve in that way only, otherwise you won't get correct answer. Okay, so you solve in the method that was solved. Don't solve in this method whatever was discussed into this class. These are highly simplified version, just for pure understanding purposes only, basic understanding purposes only. For exam purposes you need to solve by the method that was discussed in the class, the detailed method. Okay, so I suggest you practice these problems again using those detailed methods. Okay, if you have any problem you can ask me anytime, you can mail or contact me anytime. And in the next class also so one of you had discussed in the asked me in the this previous week that this question 14 and 15 of week 4 assignment 2. Okay, so I hope you are able to solve it. If not, these will be very easy, extremely easy problems. Okay, I hope you are able to solve questions 14 and 15 from assignment 4. If not, you tell me now, or you can also tell me next class. I will tell you the solution. Also, it is very easy, extremely easy. Okay, just 2 line solution. All right. So with this, we will be ending today's class. So thank you for attending. So have a good night. Okay. Thank you.